All right, today I will talk about the character of an induced representation. So let us first recall the definition of an induced representation. We begin with a finite group G, finite dimensional complex representation V rho of G, and let W be a H invariant subspace of V. So then what we considered rho H is the subrepresentation of rho to H. Sorry, rho H is the restriction of rho to H. So I think from now onwards we shall use a notation for that, so that I don't have to remind what this notation means from now onwards. So let's use this notation of rho. In fact, some people they don't even put the bracket. Okay, so now then we consider theta to be the subrepresentation of this restriction on W. So this is a representation of H. So we say that this W theta induces V rho, which is a representation of G, if V happens to be the direct sum of W sigmas, where for each sigma, W sigma is defined to be the G in sigma. Okay. So if this happens, then we will say that V rho is induced by the W theta, and that's how we defined when a representation is induced by a subrepresentation of the restriction, and then using that we defined when a representation is being induced by another representation, not necessarily a subrepresentation of the restriction. Then in the last class in the last video, we proved the universal property that shows that given any representation that induces a unique, given any representation of H that induces a unique representation of G, and the unique means unique up to unique means up to isomorphism of representations. So since we have established the uniqueness, existence and uniqueness, so therefore it demands a spatial notation to be reserved for it. So let's use this notation in the GH theta. So in the GH theta denotes the induced representation induced by theta. So yeah, so from now onwards, for our convenience, we will assume that if rho is induced by theta, then theta, then if again, so if from now onwards we assume that if W theta induces V rho, then we will assume that W is actually an invariant subspace, H invariant subspace of V. This is this is not any loss in generality. This is not making any loss in generality, because we know that there is a subspace, H invariant subspace of V, which such that the representation of restriction of rho on that is isomorphic to theta. So once we identify these two isomorphic representations, then we can safely assume that this is W is contained inside V as a subspace, and W is invariant under H. Okay, fine. So so now the question that we want to ask is, suppose we know that W theta induces V rho, then whether there is a relation between their characters. Or in other words, can we determine the values of chi rho from those of chi theta? So this is not this is in fact quite expected, that because since the representation, this representation induces that, so certainly this character should be in a sense induced this character as well. So that is what we will see now. So let first take a G in G. So we now in order to compute chi theta of G, we have to, by definition, we have to compute the trace of rho G. Okay, so recall that we have assumed that so this representation induces that representation, and in fact V is an invariant subspace, H invariant subspace of V, W is an invariant subspace, H invariant subspace of V. So therefore it is therefore V can be written as the direct sum of W sigmas. Now what we do is we rather choose a complete set of representatives. That means from each coset we will choose one representative and fix this set beforehand, fix this in the beginning. So once we fix such a set, we now write the above as rho R W, R belonging to R, that we can write. Okay. So now, so so writing this using representatives here is going to be quite helpful in the computation of trace of rho G. So yeah, so let's try to compute that. So in order to compute the trace of rho G, what we have to do is we have to take a basis. We have to take a basis of V, and corresponding to each basis element, let's say small v, we have to look at the coefficient of small v, we have to look at the coefficient with respect to so for every small basis element small v, suppose we have to well let me repeat again so that you should not feel that you are lost. So you have to first consider a basis of rho G, right? And we have already seen that which basis you choose, that doesn't matter. So we will choose a basis according to our convenience. So let's do that first. So for each row RW, let us choose a basis, let's say BR. Okay. So since this is the V is the direct sum of all this, so union of BR, where R is in R, gives a basis of V. Okay. So what we have to do now is for any R and for any, let's say V in BR, we will look for rho GV, and for, in fact, more precisely, we will look for, so rho GV can be written as a combination of elements from VR. In particular, in that expression, since V is present here, so in this when we write this as a linear combination of elements from this basis, so the V will appear, since V appears here, so we will have a coefficient of V in this expression. So for each V, we pick up that coefficient and take their sum. That is what going to give me the trace of rho G, right? That's how we compute. Okay. So therefore, our job is to find out the, so as I said, our job is to find out for each R and for each V in VR, the coefficient of V in the expression of rho GV as a linear combination of elements from, let's call this set B. Okay, so this is what our aim is. Okay, so let's see. So once we apply rho G on some summand, rho G, rho R, W, so it just becomes rho GRW. Okay. Now GR again belongs to some coset of H, and since R is the complete, this R is a complete set of representatives. So GR so for this GR I have, let's say, RG in R, such that this, so RGH. Okay, because this is what the this is a complete set of representatives. Yeah, RG of H. So there is a from since it's a complete set, so this RG is unique. So now we can write this as rho RG W. Okay, fine. Now we have first observation is, if RG not equal to R. What does that mean? That means rho G, when it is being applied to this summand, it is actually shifting that to a different summand. Okay. So if that happens, then for every V, if and for an R, if for an R this happens, then you see for every V in BR, the coefficient of V in this expression has to be 0, right? Because the elements of, so rho GV is now a member of this. So therefore in that expression, so therefore in the expression of rho G, only the vectors of B rho G, BRG can have non-zero coefficients. Okay, so therefore here for if R is such that R not equal to RG, then for any V, the coefficient of V in the expression of rho GV is 0. Therefore these basis elements, if R is like this, then the basis elements, that is BR, the basis elements BR, they do not have any contribution in the computation of trace of rho G. Okay, so so therefore since they don't have any contribution there, so therefore from the sum of these things, I can simply ignore those V's which belongs to an R, which belongs to BR for an R like this. So in view of that, what we now have is the following, that, and also, so yeah, also we will make one more observation here. So the observation 1 and observation 2 is just a complementary to that. So if R equal to RG, then you see here what happens, that rho G applied on rho RW, so the image has to be, say, rho RW. So it is actually a map from rho RW to rho RW. Okay. So since this is a map from rho RW to rho RW, then for every V belonging to BR, if I compute the coefficient of V, if I compute the coefficient of V in the expression of rho GV as a linear combination and then take their sum, then that is just nothing but the trace of this operator, right? Because trace is defined like this. So for any V in V, we have to consider the coefficient of B in the expression of this, and I take their sum. So that is just coefficient of this operator. So in view of this and this observation, what we have is, so chi G, which is nothing but trace of rho G, is nothing but trace of this restricted operator. So let's for the time being denote this notation, that rho G comma R. So this is nothing, rho G comma R, where R belongs to RG. Okay, because when R doesn't belong to RG, those terms, so R doesn't belongs to RG, so those terms we can simply ignore. And when R belongs to RG, then the sum of the coefficients for each basis element V of BR for a fixed R becomes just the trace of rho GR. So now it becomes the sum over all such R. Okay. So now we have to compute this fellow, and the computation of this fellow is also quite easy. We just have to make an observation. So you see that, so rho RW to rho RW, we have rho GR. Remember, rho GR is nothing but the restriction of rho G on rho RW. On the other hand, I have rho R from W to W, W to W. So then what is this map? Can we just see immediately? That's very easy to see. So here it so what is this? First, let's from here to here. So rho R being applied on, this is just rho G, right? So then so this is basically rho G. So from here to here, from if we come here, from here to here and here to here, what we have is just rho GR, rho GR, and here we have rho R. So therefore we observe that we write that rho R times rho R inverse GR. Okay, R inverse GR. That's fine for any G and any R. Okay, now we realize that R in, since GR belongs to RH, GR belongs to RH, as by our assumption R is in RU, right? If R is in RU, that means RG means this, RG means R. So that means GR belongs to RH. So if GR belongs to RH, then R inverse GR belongs to H. So this fellow belongs to H. Okay. So rho of an element H. So what we have here is nothing but rho of an element in H. So rho of an element in H, and this operator is being restricted on W. So this is exactly the, so this is exactly what theta H is, where H is nothing but R inverse GR. Right, to see what we have done is, let's put H for this. Now what we have, rho H, which is operator, original operator from G to G, but now we are restricting that from W to W. So for an H, we are restricting rho H from W to W. So therefore, by definition, this is nothing but theta H. So this just shows that this diagram commutes, and thus therefore theta can be written as, so theta H becomes basically nothing but this, the theta H becomes rho GR compose rho R and then rho R inverse. Okay, so just theta H is nothing but the, this linear operator is nothing but the conjugation of this linear operator, but by these two. So that immediately shows that the trace of rho GR has to be trace of theta H. So therefore now we recall this formula. So therefore what we get now is chi rho of G is nothing but chi rho of G is this R is in RG. So chi theta, because the trace of this is symmetric, so chi trace of this, so chi theta of H, and H is this, so chi theta of R inverse GR. Okay. Okay, so that shows that we now, in view of this, we see that we can write we can determine the character or value of the character at the point given G by the values of the characters of chi theta. But we will now also bring that in a much more neat form. Recall that if R is in RG, then any T belonging to RH. So if R is in RG, then for any t belonging to Rh, what happens that R inverse t belonging to H. Okay, so since this is a class function, so just this term chi theta of this is same as T inverse R, T inverse R, G, R inverse T, right? Agreed. So for any R, so for each R, if we take any T from any T belonging to RH, then this is what it happens. So that means we just have this, yeah. So that means what we just have is, just a minute, I think yeah. Okay. So therefore, what we have here, let me just simply simplify this term, chi theta T inverse G T. Okay, T inverse G T. And this is for any T belonging to, so this is for any T belonging to RH. Okay, so T belonging to RH and R belonging to RG. Now we will make this index set much more clear to us. So R belonging to RG means GR belongs to RH, right? So that means, as we have seen, R inverse GR belonging to H. Okay, so since R inverse be, so yeah, so therefore this index set in the very beginning we can simply replace as R in R, such that R inverse GR is in H. Okay, we can simply change it here, and from in view of that we see that here we can change it simply as T in G, such that T inverse GT belonging to H. Okay, because if T inverse GT belonging to H, that means so yeah. So if T inverse belonging T in G, so that T inverse belonging to in G, then this two index set, actually you have a correspondence between them. So thus we have the following formula for chi rho of G is basically, so I have to make some, yeah, so there is a small mistake, so far it is fine. Now you see for each T, so here, because of for any such things we have these many repetitions of terms here, like, because for how many terms are there here we have exactly, or number of terms here are exactly order of H many terms. So in this sum, so for the way we have observed that whatever you have here for any T we have this. So thus, so this is nothing but the average of this for T average of this for T belonging to RH, right? Again, well, I think I should explain it more to you. Try to observe that why these two sets are same. So this chi theta R inverse GR isn't it same as every all T in RH chi theta T inverse GT, right? No, not yet. I am not yet done, and that has to be divided by order of H. Because for every T in RH, this is same as this. So basically, if you don't divide it, then so since each of these terms is just this, right? For every T in RH. So therefore, this is just an average of sum of all these. Okay. Now, since for H, RH, these RH, they constitute all the group elements such that this happens. So therefore now since each of this term is now replaced by a sum like this, so therefore this whole sum is now replaced by this. Okay, so therefore thus we get the value of the induced character is the linear combination of the value of the induced character is nothing but the linear combination of the values of chi theta on the intersection of the conjugacy classes of G with H. This is what we have now. This is what the expression for this induced character, value of the induced character at the point G. So we first consider the conjugacy class of G, take the intersection of the conjugacy class of H, and in that intersection, you just take the values of the character and then just consider its sum. Okay. So the main point is realization that each of these terms is basically this, and then using that, changing the index set to that. Okay. So R such that this happens. So the sum taking sum over all R such that this happens, and they taking sum over T's for that this happens. That there's actually same. I hope that now it is clear to you. Okay, so we will finish with one more thing. So basically we'll be generalizing that. So let F be in a LH. So F is a class function of H. So from that, let us define a function called F inverse. I want to define it for from G to C. So F inverse G is from the since character is in particular a class function, so from a class, so if we somehow wanted to extend this for class functions, so the way I should define it, it must be the following: as expected, T inverse GT in H chi theta, T inverse, sorry, not chi theta. Okay, so let's for each class, sorry, I made a small mistake. For each class function in H, Z of LH, we define F prime to be this, and as expected that, so well, first let me fix a notation for this. So starting from H, so we write F prime as the induced, so function induced by F. So we use this, or simply when there is no confusion, we simply write int F. Okay. So what we have just seen is when F is a character, when F is a character of so when F is a character of a representation of H, when F is a character of a representation of H, then F prime becomes a character of its induced representation. Okay, so when thus if F is a character of H, then int F is also a character of G. Okay. So since every character, so since every F in the center of LH is actually a sum of linear combination of characters of H. So once we break H as the linear combination of characters, then each of this summand will be a character of some induced representation of the corresponding induced representation. So let me again just quickly write that for you. Suppose F is in a sense, let's say M1 chi1 plus 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 mk chi k. Then int F, when we write that, it will be just so when F is replaced by this, so then you can break this sum into k many parts, and from there it will be clear to you that each of this summand is the character of the corresponding each of is so a typical summand like ith summand. So the summand corresponding to I is going to be the, well, let me write that's better. So int F is nothing but going to be the mi I from 1 up to k mi times a sum like this 1 by, so I'm not writing it further. So here just chi I will appear. So what is this? This is nothing but the character. So this is nothing but the induced character, the character of the representation induced by chi I. Okay. So thus the entire thing becomes, int F becomes a linear combination of characters of G. So that's again a class function. So therefore what we have just proved that earlier, so in view of this observation, so starting with the character, if we just take such an expression that becomes the character of a representation of G, namely the induced representation. In view of this observation, what we proved that holds also for class functions. So what we had earlier, now that we have that extended to the class functions. So now I just leave you to check that X goes to this F goes to int F is a linear map from ZLH to ZLG. Okay, so therefore, yeah, so from the characters we have extended, so from the characters we have extended the extended thing to any general class function. So now this formula that now this formula we see that it holds for any general class function. Okay, how we prove that? We just use the fact that H is the linear combination of characters. So then this entire sum breaks, and each of the parts turns out to be a character of some representation of G. So therefore F prime becomes just the sum of, so F prime, which is denoted by int F, becomes the sum of characters of G. So therefore int F becomes a class function. So not only taking a character, considering a character of H and take a sum like this, not only just considering, not only just for taking a character of H and then considering a sum like this gives us a character of G. That also, I mean, yeah, let me finish. So not only considering a character of G, character of H, and then considering a sum like this that gives us a character of G, that also happens when we do it for class functions, when we do it for any class function on H. Okay, so what we've seen here, we have extended to class functions. Okay, so with that I will stop. In the next video we will talk about Frobenius reciprocity law. Okay.